Everyone. In this video, we will be talking about distribution functions. In the last video, we talked about random variable. So we will be defining a distribution function in terms of random variable. So why do we call it a distribution function? It's because it distributes the data and it helps you to study the distributed data. And from this distribution function, we will be making PDF probability density function and probability mass functions. And under these um, area under the curve would be telling about you like the probability of that interval and so on. So that's like this distribution function helps you to like find probabilities under a curve. So like these kind of things tell us about the word distribution function. So let us start. Um, with a random variable x, we associate a function called cumulative distribution function of x. The cumulative distribution function or CDF of a random variable x is denoted by fx of x is defined by this. So this is the definition. So this is how we define distribution functions. It's cumulative distribution function CDF. Let us take an example and find the CDF of that random variable. So x equals to the number of hits and toss fair coin. How many times? 3 times. Then we will have like 0, 1, 2, 3. For 0, we will have only one outcome. All heads. All tails. And for 3, we have all heads, which is also just 1. And for 1, we will have 3 out of 8. For 2, we will have 3 out of 8. So this is the table. Right? So let us try to find probability of x equals 0. Okay, this is already given from here. Consider a tossing coin, fair coin, and let x equals to the number of heads observed. X belongs 0, 1, 2, 3. Probability of x is 0 and so on. So it's saying if I take x to be negative, then probability x less than 0 would be nothing, like this would be 0. If I take from 0 to 1, so let me make a number line. This is 0 and this is 1. If I make from 0 to 1, if I move from 0 to 1, including 0, 0 to 1, then what if I don't include 0 here? Assume I don't include 0 here. Then for 0, we are accountable. So answer would be 1 over 8. So if we include 0, then we are good. And here if we include 1, then we will have a different outcome than 1 over 8. So that's why between 0 and 1, we have only this 1 over 8. And for 1 to 2, we have 1 half. For 1 to 2 means what? For example, if I take 1.5. So if I take 1.5, then I will have like 1.5. If 1 is less or equal to the 1.5, 0 is less or equal to the 1.5. So for 1.5, we have like 1 over 8 and 3 over 8. So cumulative distribution will be 4 over 8, which is 1 half. So in this way, we continue and fx of 2.5 is less or equal to 2.5, which is 0, 1, 2, and this is 7 over 8. Saying now CDF is defined for real numbers x, not only for x belongs to 0, 1, 2, 3. The jumps occur at the values in the range of x, and the size of jump at xi is probability of x equals to the xi f of x xi limit x approaches xi from left, and f of x xi. So now if I give you an example here, our graph was like this. So what would be probability of x equals to the xi? So this jump is actually probability of x equals to the xi, which is, so this point is over here, fx of xi. So this is xi point. So fx xi, the upper point, then how we defined in terms of xi this point. So then we say we come left to xi, the x approaches xi from left, then we are here fx of some x naught, let's say. So that would be this number, and there we go. This is probability of x equals to the xi. So also f of x equals 0 for x to be negative. Since x cannot be negative, f of x equals, and f of x is 1 for all x is 0 to equal to 3. Since x is less or equal to the always 3. The CDF is right continuous, we just observe from the graph. At each jump point, the value of fx is the value of top of the jump. At each point, the value of f of x. Thus, limit x approaches x 0 from the right is fx of x 0. This is just like intuitively we show this. This is right continuous. For showing right continuity, this is again example, the graph of an example. Now a function fx is a CDF if and only if the following condition holds. Assume this is a CDF, then we will be showing fx is 0 and limit x approaches x infinity, fx equals to the 1 and it's non-decreasing, and it's right continuous for, that is for every x we have this. So now fx equals to the x less or equal to x, when x approaches minus infinity, the event x less or equal to x becomes impossible. So when x goes to minus infinity, then x less or equal to the x, it does not make any sense. So if x goes to 0 as x approaches infinity. Yeah, as x approaches minus infinity. Now as x approaches infinity, the event x less or equal to x becomes the certain. It covers the whole space, so f of x goes to 1 as x approaches infinity. Now for decreasing, assume x is less than x2, then this set is subset of this set. We can show that because x1 is less than x2, if we take element from here, x1 is less than x2, so hence element would be here. So hence this is a subset. Hence by monotonicity of the probability, What's the monotonicity? This is A subset of B implies probability of A less or equal to the probability of B. It's monotonicity. Thus, for non-decreasing, thus this F is non-decreasing. For the right continuity, how do we show the right continuity? Assume that xn approaches x from right. In other words, you can just write xn approaches x from right. So this is same thing. All right. So that means this is x0 and this is x1, this is x2, this is x3 and so on. Then events in this satisfy. If we have this one, then A1 would be superset of A2, superset of A3 and so on. All right. And note that intersection of all ANs would be what? X less or equal to the x naught. Therefore, by continuity of the probability for decreasing events, limit n approaches infinity fxn, which is the limit n approaches infinity, which is probability of an by definition. Now, this is a question like probability of an equals to the probability of intersection n's. This is comes from continuity of the probability. So we call this is the continuity of probability. We can just show this in Mayer theory. So it's not hard to show. And then this intersection is less or equal to the x naught, and this is this. So hence this is right continuous. For the converse, we will not show the converse. It's a little bit hard for me to show the converse. Suppose you toss a coin until a head appears. Let P equals to the probability of head on any toss. 0 is less than P less than 1. Define number of tosses required to get the first head. Number of tosses required to get the first head. When first head appears, then that's it. So x would be what? 1, 2, 3 and so on. So probability of x equals to the xi, x equals to the x. So this is x equals to the 1, 2, 3. So first x minus 1 would be failures. And then x would be the success. So x probability of failures would be, they are independent. So this will be 1 minus p power x minus 1 and then p. Because the event meant this x minus 1 tosses are tails and x toss is head. Hence, for any positive integer x, probability x less or equal to the x, some probability of x equals to the x equals to the I. Okay, we are trying to compute probability of x less or equal to the x. So we are taking x to be only 1, 2, 3 and so on for now. So probability of x less or equal to the x means I equals to the 1 to x of probability of x equals to the xi. So this would be this. Using geometric series formula, k equals to the 1 to so on. I just want to write for my understanding k equals to the 1 to n t power k minus 1 equals to the 1 minus t power n divided by 1 minus t. Alright, where t is not 1. So using that formula, we can see that you just take t outside, and this is t outside, and this is t power I minus 1 and this will be 1 minus p power x over 1 minus 1 over 1 minus p. So this would be like p will be get cancelled with p, and we will have 1 minus 1 minus p power x. So the CDF would be for x to be less than 1, this is 0. X greater or equal to the 1, this will be 1 minus 1 minus p. This is a least integer function, which says like if you have 0.3, I will give you 0. So because you are close to 0. If you give me 0.7, I will give you 1, because this is close to 1, right? So equivalently on each interval n to n plus 1, f x of x equals to the 1 minus p power n. For 0 less than p less than 1, I am really sorry for disturbance. So for 0 less than p less than 1, f x satisfies the three conditions of the theorem 1.5.3. X approaches minus infinity, f x of x is 0, that's true. X approaches infinity, 1 minus this is, that's true. And it's also non-decreasing, that's really easy to see. Fx is right continuous and it's constant on each interval n to n plus 1. No, what I was saying was wrong, because if you take 0.1, it will give you 0. If you take 0.7, so it will give you the greatest possible least integer function. So least integer function is it will give you 0 point. It will also give you 0 or 1, n to n plus 1. It will give you 0 again. All right. So let me just confirm that this is true or not. Least integer function of 2.5, let's say. It should be 2. Oh, it's 3. Really? Oh, this is least integer function. And the one I'm saying is the greatest integer function. Yeah, I was wrong. So this is greatest integer function. So it will give you the greatest number n to n plus 1. It will give you n. So it takes the jump at each top of the of each jump. For p equals 0.3, the geometric CDF is shown below. And this example is the example of continuous CDF. And this logistic distribution, we can see this satisfies x approaches infinity, and x approaches this minus infinity and positive infinity. This is 0 and this is 1. And we see that by taking derivative is positive, so it's not decreasing. Since it's continuous, so hence it would be right continuous. So that's why it's a valid CDF. Similarly here, this is valid CDF. And if you subtract f of 0 minus 1, and f of 0 minus f of 0 minus 1 is epsilon, so there is jump at 0 of epsilon length. All right, so random variable x is continuous if xf of x is continuous function of x. So we are saying the definition of continuous random variable and um, discrete random variable in terms of CDF. So if CDF is continuous, then we say the random variable is continuous random variable, and if fx is a stepwise function, then x is discrete. The CDF fx determines the probability distribution of x. For example, if you see that probability a less than x less or equal to b is fx of b minus fx of a. We can show this. Yes. How do we show this? Start from the left hand side. Probability a less than x less or equal to the b. So I want to write this as probability of a intersection a complement intersection b. I want to write this as this. So can I write this as probability of negation of x less or equal to the a and x less or equal to the b. So this is probability x less or equal to the a. Negation means x is greater than a. That means a is less than x. So this is technically probability of b minus probability of a intersection b. So this would be probability of x less or equal to the b minus probability of x less or equal to the a. So this would be fx of b minus fx of a. All right. So if p probability x greater than x is 1 minus probability of x less or equal to the x. So that's it. And that's it. So these probabilities are defined in terms of CDF, and fx negative is coming from left, and that's it. If this is coming from left, then probability x equals to the x is equal to the fx of x minus fx of from coming from the left. So thus jump of the CDF gives you the point probabilities. Let us see the definition of IID. Random variables x and y are identically distributed if for every Borel set A subset of R, probability of x belongs to A is same as probability of y belongs to A. For every Borel set A subset of R. So Borel set is like the sigma algebra generated from the open sets, I believe. So identically distributed does not mean equal is random variables, that is not necessary for that x equals to the y. If you take this example, x equals to the number of hairs and y equals to the number of tails, then you will see that probability of x equals to the a is same as probability of y equals to the a. But they are different. They do not meet at any point. The following two statements are equivalent, that is saying x and y are identically distributed if and only if x of x equals to the f of y of y. Suppose x and y are identically distributed, then for every Borel set A, probability of x belongs to A equals to the probability of y belongs to A. Taking A equals to this, then it will give you this. So hence fx of x equals to the fy of x for every x. Conversely, if fx of x equals to the fy of y, then probability of x less or equal to the x is same as probability of y less or equal to the x. So let us now take probability of a less than b less than or equal to the a less than x less or equal to the b, which is fx b minus fx of a, which we just showed from the past one. And this is fy of b minus fy of a, because these are because fx of x is same as fy of x. So this is same as this, and this is same as this, and this is same as a less or equal to a less than y less or equal to the b. So they agree on every closed sets, semi-open, semi-closed. So it should agree on the whole Borel set, because Borel set is generated from such intervals. So there we go. We are done.